We are at question 3 now, and we are looking at kind of some of our parameters. Actually, let me change colors. We are looking at some of our techniques that we learned in this kind of series of lecture: XRD, DSC, REF, PDF. So many acronyms here. So still working with these polymers, and let's actually go up and remember again that for our ranking, our D was the, or actually C was the top. So C was our largest TG, then D, then B, and then A. So let's go ahead and write that down. C, D, B, and A for our TGs. So TG ranking, it goes from largest C, B, B, then A. So all these polymers are semi-crystalline with one exception. Additionally, with purchasing 4 polymers, remember the amorphous polymer is the one with the largest side chain. So if we look back when we remember to this, our schematic, the one with the largest side chain, obviously, clearly is going to be D, which is polymethyl methacrylate, which is in fact a fully amorphous kind of polymer. So D is going to be our, so D is amorphous. So D is going to be completely amorphous. Let's see, polymer structure is critical to determine the properties of polymers. So undergraduates, there's XRD and DSC. Deal with XRD first. So undergrads feel confident. Polymer A versus polymer D, do you agree with their labeling? So we know that D is fully amorphous and that the rest of them are semi-crystalline. So I agree with these plots. So we remember semi-crystalline, again, the larger the degree of crystallinity or the more crystalline a material is, we're going to see in our kind of I versus 2 theta plots these peaks, and the number of peaks and basically how many in the sharpness of these peaks determine or indicate the presence of long-range orientational order and long-range translational order as well. If we are working instead with an amorphous polymer, like we know that we're dealing with in D, you see the peaks. Look at the this is probably what 2-3 degrees. Look at this, 10 degrees. So much wider and fewer peaks. Again, so fully amorphous. So my undergrads finally got one right. They nailed this one. Fantastic. So now they ran polymers A, B, D in the DSC, but they didn't label the plots. So we need to label these DSC curves, any key points, and then justify your selection of what's the polymer based on the structure of each polymer. So let's go ahead. So we're working with, again, A, B, and D. So let's look on this next page. So we're looking at A, B, and D. So we know that D is amorphous. These are semi-crystalline. We also know that D has the highest TG out of these 3. Then it's going to be B, and then it's going to be A. So in order to see if this is endo or exo up, I know that in order to my TG, I need to absorb energy. So if the slope goes up, that first kind of change in transition, I know that's going to be endo. So I can clearly see as I trace along this curve, flat, 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 and it absorbs energy. Again, that's our, this change in slope indicates, again, TG is a second order phase transition. TM is going to be first order. So we know that this is going to be indicated by a change in slope, whereas this is going to be indicated by this. We could also have an exothermic peak of TC as well. So I know that my largest TG should correspond to my polymer D. So actually D, and I should not have any, semi-crystalline peak. So this is my TG of D, and that's D for sure. Then I know my next smallest one is going to be D, then B. So, or actually my next, yeah, so this will be larger. So this is in fact my TG of B. This is my TM of B. And then I also have, that's it. There's no recrystallization here. For A, interestingly, for high density polyethylene, this is my TG of A. This is my TC, that recrystallization peak, TC A, and this is my TM of A. And if I integrated this curve, again, I could kind of, if I look at kind of the area of this curve, I know that I could get the delta H of fusion of A divided by H of like theoretical or 100% crystalline, and then I could get my percent crystallinity there as well. So always think about kind of the integration of that peak and what can be occurring there. All right, so I think those are all the key points on that kind of polymer, or that key points on that XRD curve. So remember, you could always get some values here by integrating, the heat of fusion released, again, that delta H that goes into our equations, you could get that by, again, integrating kind of this curve. And we could also, again, if you have the same polymer, if you have or like a similar variant like LDP versus HDP, you can kind of see the difference in that, again, how much enthalpy of fusion there, because we're only melting crystalline regions. So the larger this value is, the larger the percent crystallinity. Quick tip for an upcoming exam problem that will likely come up. So be aware of that. So larger, larger area under the curve, larger degree crystallinity. I'm so nice at giving tips. All right. So my undergrads are also interested in thermoset polymers. Thermoset will not cure unless we add heat when we mix. So there are the DSC curve as we heat up the polymer. And then, sorry, before we finish. So bad, Josh. Let's go ahead. So we know that this is going to be endo and exo. So here, let's go back to the question. Interested in thermoset, draw the DSC curve as we heat up the polymer, draw the DSC curve as we cool down the polymer from high temperatures. Draw the same heating and cooling curve for polymer C, excuse me. So one of the cool things that you can kind of do with DSC curves is you can see kind of the reproducibility and actually whether they cure or whether, again, thermoset polymers versus thermoplastic polymers. So if we look, so let's go ahead and first do our curve with thermosets. So if I do my thermoset curve, let's see, we're going to have our TG. Let's go ahead. So this is exo-endo, so be careful in those kind of curves. So I'm going to do, this is going to be for my thermoset. And then for C, I'm going to use this for C, which is going to be semi-crystalline. So I know that when I heat up first, so we know that I am going to go through my TG, then we're going to melt. I'll continue on there. And then if I cool back down, I'm going to crystallize, which is exothermic. And then I'm going to go back down here because that's my endothermic reaction. And TG is always endothermic. So that's my basically heating and cooling curve for semi-crystalline material. Now for thermoset, I'm still going to have my TG, and then I'm going to have my exothermic peak. As I cool back down, I'm not going to cure again. It's not, again, thermoset, curing is not a reversible reaction, unlike, melting and crystallization. So you're not going to see this peak occur again, and then you'll see again your same kind of endothermic kind of reaction for that TG occur. And again, you see this kind of shift here. This is called your basically delta T, not undercooling. This is your degree of supercooling. Supercooling here. And again, this is kind of a kinetic effect of basically heating and melting your polymer too quick. But again, this is a little bit beyond the scope of what we kind of talked about in this course. You'd expect to see a little bit more focus on what we focus on in class, which is this kind of basically crystallization rate and these nucleation growth types of problems. But again, it's a fun idea and fun kind of problem to know about, and some behavior of polymers that might not be as intuitive. So key thing, know how to interpret these graphs, endo, exo, and that's it. You'll be ready to go. All right, I'll see you on the next video. Thanks.